Good day, everyone. Today, I'm excited to introduce a prototype of semantic communication, a next-generation paradigm in communication systems that goes beyond simply transmitting bits. Instead, it focuses on conveying highly compressed and context-aware information tailored to a specific task. Traditional communication systems begin by converting the original source, whether image, sound, or text, into a bit stream through preprocessing and compression. The primary objective is then to reliably transmit these bits over a noisy channel. While this separation of compression and transmission simplifies the design, it becomes inefficient when the goal isn't perfect reconstruction of bits, especially under limited resources or restrict latency constraint. In recent years, AI-powered joint compression and communication systems have gained attention, showing notable improvements in end-to-end task-specific performance. The core idea is to employ an all-in-one encoder and decoder architecture based on deep neural networks, where the network parameters are optimized for a specific end-to-end task-oriented performance metric. This joint design approach has demonstrated promising performance gains for executing specific target tasks. However, these joint systems also have limitations. They struggle to adapt to dynamic wireless channel conditions and often cannot handle multiple downstream tasks beyond the one way were optimized for. To address these issues, we propose an approach based on three key strategies: knowledge-based feedback, task and channel-aware multimodal adaptive compression transmission, multimodal multitask decoder. Let me explain how our system works. The receiver starts by identifying the intended task and the required modalities. For example, if it needs to reconstruct an image, it may request both a compressed image and its texture descriptions. The receiver also sets the constraint like a target communication delay or available channel bandwidth. All this feedback information is sent back to the transmitter, which then adapts its encoding based on the task and the channel knowledge. The transmitter performs nonlinear transfer coding for image compression, followed by top K feature selection to keep only the most relevant semantic contents. These features are power scaled and mapped into analog complex symbols. Simultaneously, the keywords are extracted from the image, compressed using Lampage coding, and then digitally modulated for the transmission. Based on the resource allocation knowledge, the system dynamically assigns the subcarriers and generate OFDM symbols with both analog and digital part. This hybrid digital analog modulation scheme ensures that task-relevant information is efficiently and robustly delivered under given channel constraint. The multitask decoder first recovers those compressed image features, samples, and texture information. This is achieved using a combination of nonlinear transfer coding decoder for the image and the conventional coded modulation decoder for the text. Once raw modalities are reconstructed, the decoder enters the second stage, where task-specific processing is performed based on receiver's intended objective. For example, if the desired task is image classification, then the same recovered features and text data are input into a task-specific classification decoder. Alternatively, if the target task is image generation, then recovered image features and text descriptions are jointly fed into a generative model, which synthesizes a high-quality image with a strong perceptual fidelity. This modular decoding architecture enables flexible and efficient multimodal inference tailored to a wide range of downstream tasks. Next, we will present a demonstration of our semantic communication system prototype. We implemented a wireless communication testbed using NI transceiver module. The system operates at 2.4 GHz carrier frequency with a 20 MHz bandwidth, enabling real-time wireless transceiver experiment. The transmission frame structure is designed in accordance with the IEEE 802.11n standard. In our experiment, we considered to send an image. Conventionally, transmitting a single image represented by approximately 1.5 million bits would require around 13,000 OFDM symbols, resulting in a transmission delay of roughly 52.3 milliseconds. In contrast, our proposed semantic communication method can transmit the same image using only 85 OFDM symbols, which correspond to a delay of just 0.34 milliseconds. This translates to an approximately 154 times reduction in transmission delay, demonstrating the significant efficiency gain achievable through task and context-aware semantic communication. We evaluated performance on 3 tasks under low latency constrained communication scenarios. The first experimental result focuses on image reconstruction task, where no texture information was used. Under both packet delay constraint, our experimental result demonstrates that the proposed semantic communication architecture outperforms the conventional approaches in terms of PSNL. The second experimental result focuses on image classification task. Under both packet delay constraints, our results shows that the proposed semantic communication method achieved the highest classification accuracy compared to traditional approaches. The third image generation task, which utilizes both compressed image features and texture information for reconstructions. Notably, when packet length is severely limited, existing approaches fail to generate image with acceptable quality. In contrast, the proposed methods successfully reconstruct images that preserve the semantic contents of original input under stringent bandwidth constraint. In summary, we present a knowledge-based feedback architecture designed for task and channel-aware adaptive multimodal compression and transmission along with multitask decoder. Experimental result confirms that the proposed approach effectively combines the strengths of 2 existing methods and shows some potential for delay-sensitive and task-oriented communication system. Thank you for the attention.